this is the, I believe, seventh or sixth of our webinars, and we are pleased to have Professor Jimmie Oxley and Dr. Miriam Fico present this webinar entitled, as you can see, on Mobility Spectrometer, One-Stop Shopping for All Detection Needs. SMITS has been part of our community since the first ADSA, and has been an active member of our Industrial Advisory Board for 4 years and working with Jimmie closely for the last year and a half. And with that, I'd like to hand it over to Dr. Oxley for the presentation. Thanks everybody for joining.
We gave this a cutesy title. I'm sitting here with graduate student Al, who is really the pioneer of this technique, and it's a twist to an older technique called paper spray. So let me share with you the first slide. And this slide, of course, is some old information. I had a chance to look at the names on the screen. So this is pictures of IMS guts, which have been around for a couple of decades now, that these particular pictures have been available. And then we see a picture of the type of swabbing that may or may not be done at checkpoints. We think airports first, of course, but there are many other checkpoints that rely on IMS to protect their customers. The IMS shown here is using a nickel 63 to ionize the sample. The analyte will not go anywhere if it hasn't been ionized. More modern IMSs may use a corona discharge approach to get rid of all the complications of having a radioactive compound on the facility. So the diagram here is shown just to talk about how the general principles that we're looking at. Sample is obtained by swabbing, down here in the picture. Swab is put in some sort of an inlet. This varies with the manufacturer. And this is one of the oldest versions with a clamshell sort of look, where the sample swab is then heated up, driving your sample into the IMS, where it is ionized and perhaps reacted with a dopant to help move it along in terms of charging, and then move through this drift tube with a counter current of often air. And then you have your detection. The problem with all this, and it's gotten out to the airport fairly rapidly compared to, say, mass spec, which has a lot of similarities to IMS. IMS differentiating by particle size as the swarms go through the IMS, and mass spec by a charge mass ratio. But in either case, you have to have a charged sample to move through here. And of course, none of this works if your analyte didn't enter your IMS. And that's what this talk is about. So we are using paper spray in this fashion. Paper spray has been around for a couple of decades now, where your sample is sitting on a piece of paper. Doesn't have to be paper, we've shown, but I saw a surface that is fashioned into a point. So I'm moving my cursor. I'm trusting that you can see my cursor. I've given enough of these that I think I've gotten over to trying to point with my fingers, which doesn't work well at all. But this is fashioned to a point. You hope that your analyte is somewhere here. This has been probably used first with biological samples that tend to be kind of messy. Then you have two aids to help your analyte move forward off the paper into whatever your detection scheme is. And in this case, it's the inlet of IMS. That means that you're going to put a voltage across your sample, and you're also going to add solvent. And we've been trying to make both of these practical for use in IMS. Obviously, if you have a large facility, this can be done, and I will show you how we are doing it presently. But can it be done in a more modest checkpoint? And that's what the adventure with Smith is going to be talking about. So once again, there's three components: shaping the swab into a acute angle, adding a voltage so that there's a voltage being added to your sample, and a analyte. Now and a solvent to solvate your analyte. That's all about how the analyte comes off of the swab in your solvent mix, where the charge transfers. I'm looking to see if I put that in. I don't think so. In this Taylor cone that comes off here. And as your solvent evaporates, your charge is transferred to your analyte. So even though we've stolen this picture, there's no longer a need for any kind of ionization inside the instrument. The ionization is happening right here up front. Your solvent is being removed, leaving the charge behind on your analyte. And this is an alternate way to heating, to getting your analyte into your IMS or mass spec. And I think we have a picture of several different devices we've tried it on. We've certainly tried it on this portable mass spec. And we have three different benchtop IMSs that we have worked this with. This also shows that we've tried other swabs. It doesn't have to be paper. Paper, of course, is cheap, and a lot of TSA swab material is paper. But we've tried all of these other matrices, and it works to varying degrees to use them to be our swab, our pointed swab. Here is an example of what we're using here. I'll go back one slide. What we're using here is we're taking our very old atomizer, taking the little clamshell off, for those of you who are familiar with this, and I know a lot of people online are. This is what's inside the clamshell. We don't need to be heating our sample. But here is our swab. You can see it's not paper in this particular case. The amount of solvent here is huge, but basically because we wanted to make it photographical so you could see it, that's not nearly the amount you need. You need much less than that. And it's also, of course, not colored blue. But again, this is about getting a photograph early on. This is how we apply voltage to the swab. And of course, it's grounded to the IMS. And you can see here the very fancy grounding setup we've had to come up with when our inlet itself wasn't metal to work with. It can be very small swabs. We've looked at various angles. The best, of course, is quite an acute angle here for helping to form the Taylor cone with your analyte. More pictures here. Oh, yes, I do have a picture of how the electrostatic ionization, electrosphere ionization is thought to pass charges as you form your Taylor cone, and the charges are left behind on the analyte. And I just glanced at my time, so I won't go into that, but that is a well-known ESI technique. Here's a picture of our lab with various mass specs. We've tried it on more than one. You'll see a more up-to-date picture in just a minute. So we've moved from the IMS in the previous picture to a large LCMS because frankly, we wanted to look at analytes that weren't part of the library of the IMS. Therefore, we needed to go to the mass spec to confirm that we saw the analytes we thought we saw. So here they are. We've got a stand. In this case, it's a bunch of boxes. This is applying our charge, and here is our sample again going into our large mass spec. Here's the result of that. We have both the mass spec by normal ESI infusion, look at TNT, and here's the use after the ADI, we call it ambient desorption ionization technique. And you can see that we see TNT perfectly well in each case. Picric acid. RDX, we're seeing the chloride adduct, and that's something I forgot to mention earlier. That since you're adding solvent, and here we usually use methanol water, you can also have an adduct-forming ion present. Here's tetra with the nitrate adduct. So the top one in each case is the normal mass spec that you would be looking for in your LCMS, and here's what we see with ADI with our technique. The winner here is looking for chlorate that would be hard to do any of the low volatility materials by IMS. That's why it says one-stop shopping now for IMS, because we can get the involatiles in because they don't have to get in there by heating. They get in there by ionizing outside the inlet. So here's chlorate and some other examples. Another look. I think I will move on looking at the time. I want to get to the results here on the IMS. Now, those of you in the know I needed to cover up the alarms, but you can see that I was getting a alarm here for TNT, showing you that I'm really not getting one if I don't apply the voltage. And it's not that I have TNT contamination, it's that I have applied voltage, and this is the floating voltage here to get my TNT peak, and detection of a whole bunch of other materials. Now, chlorate, you would not have believed me if I hadn't shown you the mass spec first, because there's no alarm for chlorate, because the mass specs normally can't do chlorate because it can't be volatilized into the mass spec. And this is the wonderful part about ADI, is you can get volatilize the samples that aren't normally volatilized without raising the temperature to the point you kill all these other species or drive them off the swab completely. Here's our most recent picture of what's going on. Now we're using an XLM's IMS right into our mass spec, so we don't, so we can prove what the IMS look is like on this, and then look at the mass spec as well. So, and you can see we've got just a little bit more sophisticated each time we work on it. Here we're looking at just using a corner of a swab rather than any shaping algorithm, because we're trying to make this as practical as possible. However, we suspect that you won't duct tape the inlet onto your IMS, which is what we're doing here. And then I'm to my last slide, which means that Miriam is going to get to take over here in a minute. I guess I've rushed through more than I need to, so now I slow down again. Here's the method and its advantages for using ambient desorption ionization for these materials that require too much heat to drive into your IMS or even your portable mass spec under most situations. They can use any kind of swab you normally use, but what you do need is a sharp tip. As I've shown you, we think we can get away with just a corner if these are normally shaped. You can look at both liquid and solid samples. That's not an issue. The voltage, because there's already a voltage generator in most of these IMSs, doesn't have to be external, as we've shown in the picture. I'll go back to the picture just here for a moment where we're applying this. You can certainly use the internal voltage that's already available in most instruments. It's just until we start working with having Smiths do modifications, we can't access that at the moment. So our pictures remain using an external outside application. The solvent, we're still thinking about how making that easy for you. At the moment, we're using a very small amount through a syringe and a syringe pump. The ions are easily applied, whether you're using a portable IMS or a portable mass spec. And it goes through, as I've said already, the use of the voltage that's present in the IMS. And no other type of ionization is required any longer. So that kind of completes, except for this last one, application of dopant. I know with LCMS, we have a huge advantage when we can provide chloride or nitrate or ammonium, depending on what kind of ion we're looking for. And yes, this method is applicable to positive or negative ion analysis. I didn't mention that, but yes, it is. We're very excited to be starting to work with Smiths so that we can actually access the inside of the IMS. And with that, I think that I stop sharing and let Miriam from Smith share. And then maybe if you're asking me questions, I'll be back on. So I'm going to stop sharing.
So I am going to start talking about the IonScan 600. This is a IMS-based device that Smiths Detection has been developing and producing. Basically, what it is a lightweight, non-radioactive explosives trace detection. So it does explosives and narcotics, and it's also portable. The reason that we like it is because it is non-radioactive. It's highly sensitive, and it also has been certified by many of the major regulators across the world. And we have endeavored to improve the training and low cost of ownership on the device. So just a couple of key technical details. The ionization source inside of the IS-600 is a non-radioactive ionization source with a robust design, so meaning that it will last for a while in the field and non-radioactive like older IMS devices that we have fielded. The engine is a single drift tube. However, we still are able to analyze both positive and negative ions through it. We have a regenerative air purification system, so there's no consumables with that. The swabs that we use for this have a proprietary coating, and you can sample surfaces and other points of interest with either using your hand or a wand. There's no moving parts for the sample insertion, so that improves the reliability. And as soon as the swab is inserted into the detector, analysis begins automatically. And we've also improved clear down times. As I mentioned before, we can do both explosives and narcotics, so we can look in both ionization modes, which should help us with looking across the chemicals of interest that we are looking at for this project as well as for future projects. As I said before, it's lightweight and portable, so there's a small battery inside of it that allows it to be moved from one location to another. And we've tried to minimize the amount of consumables that we have. So we can use these single-use swabs. So that ensures that the detector remains clean, and the surfaces from which we sample also remain clean. The wand sampling allows the user to extend their reach, and it also protects the screener when they're working inside of bags or crates. So either method of sampling is available to the users. Basically, the detection capability of the IonScan 600 is in the picogram, nanogram range, and the false alarm rate is less than 1%. This has led us to get certified by major aviation regulators, as you can see here. So just a summary of the IS-600. Basically, the sensitivity and reliability are something that we were really shooting for with this system, as well as improving the ionization source from radioactive ionization source to non-rad, and allowing it to be fully operational on batteries so that it can be moved around if necessary, as well as allowing for both positive and negative detection so that we can look at both explosives and narcotics. So that's all that I have to say. And yes, we are also very excited to be working with Jimmie and see what we can come up with.